Okay, why is it gray again? Okay, I guess that's the thing now. All right, so odd functions, symmetric with respect to the origin, and then I give you a test. Test f negative x and see if that's equal to negative f of x. All right, so that's kind of a strange thing to say, but it's really pretty user friendly. So let me show you. If we just focus on the left-hand side, f of negative x. That's telling us everywhere that in our original function that we have an x, replace it with a negative x. All right. So everywhere we have an x, replace it with a negative x. Oh, I took the, dang it. There we go. That's a little bit better. Get rid of that stray negative x in a sec. Would have been easier to write instead of what I just did. Anyway, we're going to simplify this and see what we get. All right. If we get something that is exactly the opposite of the original function, then we're looking at an odd function. That's all there is to it. So looking to see if the result is the exact opposite of f of x. All right. So I'm going to cube the negative x. All right. Well, if I cube a negative, the result is negative. Just like when I square a positive, square a negative, the result's positive. There we have rules for cubing also. So if I take a -1 and raise it to the third power, the result is a -1. If I take, well, a positive and raise it to the power, you expect that the result would be positive. But if I do that for a -2 or a -4 or -100, it doesn't matter. The result is always negative. All right. So take a negative, raise it to the third power, the result is always going to be negative. All right. In fact, if you raise a positive number, and I'll actually just note this for you. So raise, oh, what did I say? Positive? I meant negative. Negative number to odd power, result is negative. Raise a negative number to an even power, the result is positive. All right, those are the kind of things like, could you survive the rest of your life without knowing those properties? Yeah, probably. Survive the rest of the class. Oh, why did I change that? I don't know. I'm trying to walk and chew gum at the same time. Even power. This is the one I wanted to change to positive. Yeah, you could survive, but it's nice to know because it'll shorten the amount of time it'll take to do some problems. Now, I can tell you that in calculus, so when you're sitting in calculus and you're learning about areas and integrals and all that stuff, you'll find that this page is incredibly important. So these little properties that I'm sharing with you, and also the even, odd, and symmetric and all that stuff, that it'll become incredibly important. All right. Might not feel that way for now, but down the line it will be. All right, so negative x to the third power becomes negative x to the third power. 2 times negative x is negative 2x. All right, so the original function had 2 positive signs. It was a positive x cubed and a positive 2x. My new function has a negative x cubed and a negative 2x, right? It is the exact opposite. So f negative x is the exact opposite of f of x. Therefore, 3 dots in the form of a triangle means therefore. You can write out the word if you want. Therefore, f of x is an odd function. All right. I'm not sure what that graph is doing there. Actually, for both cases, these are not the graphs. I don't know if I was paying attention or not when I did this. I mean, it clearly wasn't. So let me show you what the graph of f. Actually, let me wipe this all out real quick. F of x is equal to x cubed plus 2x. So this is what the function should look like, which clearly and obviously is not what you see on the paper on the page. So yeah, I botched that somehow. I don't know what's going on. Just playing around with the domain a little bit. So this is what the graph should have looked like. I'll take that, of course, as a typo because it is a typo. I'm just gonna get the heart of the graph. So anyway, the way this works in terms of a non-algebraic approach, so I'll just save it. I want to mark up this diagram real quick. Paste. What we're looking for is symmetry with respect to the origin. And what that means is that if I take any point and reflect it over the origin, it'll end up as another point on the graph. So for example, this point right here has coordinates 1, 1.5, it looks like. I mean, it's scaled, but if we're just kind of using our imagination, it's 1 over 1.5 units up. All right. So 1 over plus 1.5. And like I said, it's a scaled graph, so it's actually going by 2's on the y-axis, but that's not really important for what we're trying to get at here. All right. So that's great. Now, if I take that same exact movement, but do it in the exact opposite direction, will I also get a point on that graph? So instead of going to the right 1 unit, I'm going to go to the left 1 unit. So the exact opposite. And instead of going up 1.5 units, I'm going to go down 1.5 units. If I end up with, in every case, a point on the graph, then it's an odd function, right? So I could grab any point I want from one side. So let's say I go over 1.5 units and up 3 units. Can I go to the left 1.5 units and then down 1, 2, 3 units and end up with a point on the graph? And the answer is yes. All right. So if you have that symmetry through the origin, then you're dealing with an odd function. So it allows you to just do a quick visual inspection and determine that what you're dealing with is an odd function without having to do the algebra. All right. Another nifty trick, it's just hard to do with the technology because with the auto rotate and everything like that, if you look at a graph upside down and it looks exactly the same as it does right side up, then it's an odd function because it would automatically be symmetric through the origin. Right? So basically flip the page over. If it looks exactly the same, starts low, ends high, then you're dealing with an odd function. Right? So that's kind of a nifty trick. For the even functions, the process is exactly the same algebraically. So that's kind of nice. What you're looking for is different, right? So you're looking to see if the result is exactly the same as the original function. So I'm just going to do a little copy paste action here. All right, so you're looking to see if the result is exactly, I guess I need purple again, the same as f of x. Now here it's saying f of s. I'm kind of annoyed at myself for doing that. So I'm going to make all these s's into x's, and I'll take that as a typo. All right. So I'm going to rewrite my original function, replacing every x with a negative x. I forgot my 3. Then we're going to simplify. Another half hour. So I'm going to take every one of those negative x's, in this case, there's only 2 of them, and raise them to even powers. That's what I was talking about before. Raise a negative number to an even power, the result is positive. Right? So in this case, I'm looking at an x to the 4th, back to red, plus 3x squared plus 7. All right. F of x, I'm sorry, f of negative x is exactly the same as f of x. Therefore, f of x is an even function. All right. So it's kind of weird because personally, I'm not big on just rules for the sake of rules. So I'll explain very briefly because I don't want to take too much time and I don't want to bore people too much. But I don't like just giving rules without giving a sense of where the rules are coming from. So what's happening here when we replace x with a negative x is we're creating an equivalent movement in the negative direction. All right, so let me see if I could show you very quickly what that would look like. So I'm going to just plot a point, and it's really not, it doesn't really matter what I'm typing in, it's just the visual is going to matter more than anything else. A comma f of a. Right, I just need a point that'll slide. All right. And then negative a comma f of negative. All right. So what's happening here is we have 2 points that are reflections of one another. All right. But more so, it's the a value that matters, or the distance away from the y-axis. So I have this one at, we'll say, I'll just get it to 1 unit from the y-axis. It's also going up a little bit, but that's not important. All right. The fact is that I have my green point 1 unit to the right of the y-axis. All right. Correspondingly, by this definition, by this rule, I must have another point that's going 1 unit to the left of the y-axis. All right, so if I move this to 2, to the a value of 2, actually, let's make it 1.6 because that's where it landed. 1.6 units to the right, if I plot a point, then I would necessarily also have to have a point by this rule that is 1.6 units to the left of the y-axis. All right, so what's happening here is if we get an opposite relationship in the y values, that means that the distance above the x-axis for the green point is the same as the distance below the x-axis for the black point. All right, and that is the definition of origin symmetry, which forces it to be what we call an odd function, right? As opposed to this other equation, x to the 4th plus 3x squared plus 7. I'll just zoom it out a little bit. You could see here that the points are on the same level. First off, this looks very symmetric, right? If we're calling an even function something that's symmetric with respect to the y-axis, meaning the y-axis is the fold in the sheet of paper. When you fold those two sides onto one another, they match up perfectly. Then these 2 points would necessarily have to match up perfectly. But you could also see visually that no matter where I put my distance away from the y-axis, the green and the black point are always at the same height. All right, and that's what we're testing for here. We're just doing it analytically. We're doing it using algebraic processes. All right, but the graphical approach kind of tells a better picture, tells a better story. All right. Now, there are shortcuts galore, but you kind of want to be looking for shortcuts first, and then, well, really just look at the directions on any assessment. If it says to do it algebraically, do it algebraically. But you look for your shortcut first to see if you can arrive at your answer, and then you go into the full-blown approach if you need to. All right. So there's a couple of ways we can do this. One would be just looking at the equation. Right? An odd function, all powers of f of x are odd. For an even function, all powers are even. I'm also going to get this graph in here real quick. All right, so you can look at any equation and determine visually, very quickly and fairly easily, you can determine visually whether or not the function is an odd function or an even function. All right, so just going back to the first question, get in there. There we are. Going back to that first question, I'll take a look at the powers here real quick. Let me just get this plus sign out of the way. It's kind of pro here. So the powers are 3 and 1. All right. We have the power of 3 and we have the assumed power of 1. Powers are odd. All right. So it's no surprise that we're looking at an odd function. I don't care about the coefficients. I only care about the powers. All right. Looking at the next one, I see a 4. I see a 2. You might look at that 7. This is always throwing people for a loop in the past. They say, well, wait a minute, 7 is to the first power. But actually it's not. Well, 7 is, but I don't care about the 7. Like I said, I don't care about coefficients. I only care about the powers of the variable, right? There is no variable attached to the 7 directly. There's an implied variable. That implied variable is x to the 0th power. All right. Any number can be written as a fact or as a coefficient of x to the 0th power, because x to the 0th power is equal to 1. Right? It would just cancel away anyway. So we have explicitly stated that the powers are 4 and 2, and we have an implied power of 0. Bottom line is all the powers are even. So again, it should be no surprise that we're looking at an even function. All right. The issue with this technique, I mean, you look at the examples at the bottom and you say, okay, well, I'm looking at you, power of 1/2. All right, well, what about 1 over x? What on earth, like, how do we handle this? Well, don't fall in love with any one process. All right. If you're looking at a polynomial, then you would say, okay, and polynomial is going to be something in this form where it's coefficient, variable, exponent, and sums and differences involved. But you could also look at it graphically. So 3x to the 4th, I'm looking at a monomial, a single-termed expression with a power of 4, which is an even power. So I'm suspecting that I'm looking at an even function. So I'll put the 3 in there, 3x to the 4th. It certainly looks symmetric over the y-axis, so this would be even. All right, so we just need a justification. And once we have a justification, we will have answered the question completely. All right, so your justification could be algebra, it could be addressing the graph, or it could be addressing the powers. All right, so I just looked at the picture here and we got it from that. All right, x to the 1/2. Get rid of that coefficient. All right, not symmetric with respect to the origin or the y-axis. So this is going to be neither, because it has no symmetry. It has to have one of those two types of symmetry in order to be an even or an odd function. It doesn't have either, so it has neither, so it's neither. All right. 1 over x. And all this fancy stuff at the bottom aside, I'm not even really looking at that. I'm just looking at the picture. So 1 over x plus 3x. Okay, we got a little bit of symmetry going on here. That's kind of strange. So we can investigate this one further. Now, I'm not sure. So I'll use the algebraic approach and see what's going on with this one. All right. So h of x can also be written as 1 over x plus 3x, just to kind of clean it up. So I'm going to write it as h of negative x is equal to 1 over negative x, which would simplify 1 over negative x is the same as negative 1 over x. 3 times negative x is negative 3x. All right. So this is going to be an odd function. Sorry, I'm being a little lazy here. So this one is going to be an odd function because f of negative x is the exact opposite of f of x. So we're looking at an odd function. Yep. So in this case, the picture kind of got me started, but I wasn't 100% sure until I did the algebra. All right. Now, if you're willing to roll the dice, you're taking a test, it's a multiple choice question, something like that, then by all means, it certainly looks symmetric over the origin, but I didn't want to take the chance. All right. X minus 2 to the second power. Oops. That doesn't have symmetry, so that's neither. The last one, I'm just looking at the powers here, a little analysis of the powers. We have an assumed power of 1. Both of those powers are odd. So this is an odd function. Powers are all odd. All right, so you kind of see, hopefully, that if I didn't get this idea across, I'll just come out and explicitly say it. Don't do the algebraic approach unless one, you're told to, or two, you absolutely need to. All right. You tried everything else and it didn't work. All right, I guess I'll do the algebraic method. Because in most cases, you can see here 4 out of 5 problems. Now, out of 4 out of the 5 problems, we're able to get the answer without doing the algebra. Right? You don't want to get bogged down with that. Right? So just keep that in mind. Very important. Let me pause this video. The last thing that we're going to do for tonight